You know, there are places on our own planet that are still as mysterious as the surface of some distant world. We tend to look up to the stars for that next great frontier. But one of the last truly unexplored realms is right here, hidden beneath miles of ice and seawater, the polar regions, especially Antarctica. They hold secrets on a theological scale, secrets written in stone and ice. For centuries, this entire world was just invisible, a blank space on our maps. But now, finally, technology is starting to pull back that curtain. And what we're finding is rewriting our whole understanding of the planet. 27%, that's the portion of our planet's entire seafloor that we've managed to map in high resolution. It's a pretty staggering figure when you let it sink in. That means over 70% of our world remains a blurry, indistinct mystery. And this isn't just about filling in some maps. It's about understanding the fundamental systems that govern our planet, everything from ocean currents to climate regulation. And nowhere is this gap in our knowledge more profound or more critical than in the waters that surround Antarctica. If you look back through most of scientific history, the seafloor around Antarctica was basically a void on our charts. We knew the continent was there, of course. We knew it was surrounded by the Southern Ocean. But the actual topography, the real landscape of what's called the continental margin, that submerged edge of the continent hidden beneath the waves and ice, well, that was mostly guesswork. It was based on sparse, indirect measurements. It was truly an unmapped world, hiding geological features on a scale we couldn't have imagined. So why was this? Well, the challenges are just immense. You're dealing with the most hostile ocean on the planet, which is covered for much of the year in sea ice. And beneath that, you have kilometers of water. And in a lot of areas, you also have floating ice shelves that are hundreds of meters thick. Trying to send a signal through all those layers to map the bottom, it's a huge technological hurdle. This combination of ice, water, and just extreme weather kept this hidden landscape a secret from science for a very, very long time. The breakthrough, when it came, wasn't from a single eureka moment. It came from a massive, collaborative effort and a huge leap forward in technology. Scientists began, in essence, seeing with sound. They used these advanced multi-beam sonar systems that were mounted on icebreakers. By sending out pings of sound and then meticulously recording how they echoed back, they could slowly, painstakingly, begin to paint a picture of the world below. And this wasn't one mission. It was a synthesis of data gathered from many different international expeditions over many years. The project was called the International Bathymetric Chart of the Southern Ocean, or IBSO for short. And when its second version came out, the improvement was just night and day. We went from a map where each pixel represented 1 or 2 kilometers, where an entire mountain might just be a single blurry dot, to pixels of 500 meters. That's a monumental leap in clarity. Vague, fuzzy outlines suddenly sharpened into detailed, complex systems. It was like switching from an old, blurry photograph to a high-definition image for the very first time. Okay, so with this incredible new dataset in hand, the next question was, how do you even begin to analyze it? Going through it manually, tracing every little feature across such a huge area would be pretty much impossible. So researchers developed a new approach. First, they built the high-resolution map. Then, they designed new computer algorithms to scan all that data and systematically pick out features that had the telltale signature of a canyon. And finally, they used what's called morphometric analysis to basically take the vital statistics of every feature they found, measuring its depth, its width, how steep its walls were. These numbers help create a really detailed quantitative picture of the entire hidden network. And the result of all this patient, meticulous work? Well, it was nothing short of astonishing. The analysis revealed something that no one had ever suspected was there, at least not on this kind of scale. A vast, continent-spanning network of massive submarine canyons, carved into the seafloor and hidden all this time beneath the ocean and the ice. The algorithm identified 332 distinct submarine canyon systems. Now, to put that in perspective, this number is 5 times larger than any previous estimate. This wasn't just finding a few new features, It was the discovery of an entirely new geological province, a fundamental component of the Antarctic continental margin that had been completely invisible to us. The scale of these things is just difficult to wrap your head around. The deepest of these canyons are over 4,000 meters deep. That's more than 13,000 feet from their rim to their floor. So, to give you some perspective, the deepest of these are more than twice as deep as the Grand Canyon. These are not minor gullies. They are colossal structures, rivaling the largest canyon systems found anywhere on Earth, whether on land or under the sea. And these 332 canyon systems aren't just isolated gashes in the seabed. They form these interconnected networks that stretch across huge portions of Antarctica's continental margin. They're like the arteries and veins of the submarine landscape, and they link the shallow waters right at the edge of the ice directly to the deep, abyssal plains of the Southern Ocean. And this really illustrates a crucial point. These canyons form a critical physical connection between the Antarctic ice sheet and the global ocean system. For a long time, we kind of thought of the seafloor as a relatively smooth, passive boundary, but we now know that it's actually a complex, rugged landscape with these deep channels that can fundamentally change how the ice and the ocean interact. So this discovery didn't just change the map, it really changes our understanding of Antarctic dynamics. As scientists started to analyze the shapes and patterns of these canyons, a really fascinating story began to emerge. A story written in stone over millions and millions of years. They found a stark difference between the canyons on the eastern side of the continent and those on the western side. And these differences reveal clues about the deep geological history of the ice sheets themselves. What's so amazing here is how the physical shape of the canyons tells a geological story. Over in East Antarctica, the canyons tend to be wide and U-shaped, with these complex, almost tree-like branching systems. That shape is characteristic of slow, steady erosion over immense amounts of time. It suggests the East Antarctic ice sheet has been relatively stable for a very long time. By contrast, the canyons in West Antarctica are shorter, steeper, and more V-shaped. This points to a more abrupt, aggressive kind of erosion, which is consistent with a much more dynamic and younger ice sheet, one that has advanced and retreated more dramatically over its history. This is powerful physical evidence for the different long-term behaviors of the two great ice sheets. But here's the thing. These canyons aren't just static relics of a geological past. They're active, dynamic features that play a critical role in the ocean today. It helps to think of them less as monuments and more as hidden highways, channeling water, sediment, and heat in ways that have truly global consequences. So you might be wondering, how did these canyons even form in the first place? Well, one of the main drivers is something called a turbidity current. The easiest way to think about it is to imagine an underwater avalanche. A dense mixture of sediment and water starts flowing down the continental slope, and it just picks up more and more speed and energy. These currents are incredibly powerful forces of erosion, and they are capable of carving deep channels into solid rock over millions of years. And it's the glacial activity pushing vast amounts of sediment to the edge of the continent that provides the raw material for these powerful flows. Now, to understand the canyon's role today, we need to introduce a key player in the Southern Ocean, circumpolar deep water. And warm here is a very relative term. It's still only a few degrees above freezing. But compared to the near-freezing water right at the surface and at the base of the ice shelves, it carries a significant amount of heat. This water mass circulates around the continent at these intermediate depths, and how it interacts with the ice is a really critical factor in climate science. And this is where it all comes together. These newly discovered canyons can act as direct conduits. They can funnel that relatively warm circumpolar deep water from the open ocean right up the continental slope and deliver it directly to the base of the ice shelves. This could accelerate melting from below, a process we know is a primary driver of ice loss in some of these sensitive regions. But at the same time, they do the exact reverse. They take the extremely cold, dense water that forms near the coast and efficiently transport it down into the deep ocean, which helps drive global ocean circulation patterns. They really are two-way highways, with profound implications for both ice stability and the global climate system. This gets right to the heart of why this discovery matters so much. right now. Our climate models, these complex computer simulations we use to predict future sea level rise and ice loss, they're only as good as the data we put into them. For decades, many of these models have been working with a simplified, smoothed-out version of the Antarctic seafloor, just because that's all the data we had. Discovering this rugged, complex network of canyons means that our models may have been underestimating just how efficiently ocean heat can get to the ice. So incorporating this new detailed topography is an absolutely critical next step for refining our predictions. So the discovery of these 332 canyons, it isn't an endpoint. It's not the closing of a book. It's really the opening of a brand new, unwritten chapter. It's answered some questions for sure, but it has opened up a whole host of new ones. It's pushed the frontier of what we know, and what we realize we now need to find out about our planet's polar regions. And this brings us right back to that first number, doesn't it? If a canyon system 5 times larger than we ever imagined could be hiding off the coast of Antarctica, what else is waiting to be found in the more than 70% of the global seafloor that is still unmapped at this resolution? This discovery is just a powerful reminder that our planet still holds secrets on a truly fundamental scale. There are almost certainly other major geological features out there yet to be found. The immediate challenge for the scientific community is a very practical one. How do we take this incredibly detailed, complex data and integrate it properly into our global ocean and climate models? It's a massive computational challenge, but it's a necessary one. Getting this right is essential if we want to improve the accuracy of our projections for ice sheet stability and future sea level rise. And that's information that is critical for communities all over the world. And finally, we're left with this thought. We have now peered beneath the ocean, but much of the rock that lies beneath the ice sheet itself is still a mystery. We know there are lakes and rivers there, but the full extent of that subglacial world is still largely unknown. The discovery of these submarine canyons is a testament to the power of exploration, and it leaves us with a profound sense of awe. And a final question. What other worlds are still waiting for us, hidden in plain sight, right here on planet Earth?